Today I'm going to talk about is generalized payments as types. When I submit the talk, I called it generalizing, so I was still work in progress. I guess now I can call it generalized. A bit about me. My name is Miao. I co-founded the Superfluid Finance. So today, what you'll hear about is a new payment paradigm where money can be instantly or continuously moved from one-to-one or one-to-n en masse, right? So this is a new concept you'll see today. And also how a Haskell toy model or reference implementation or specification for this kind of concept is written, right? So why Haskell? A pure, strongly typed, statically terse language is very best suited for domain modeling. So we're talking about the payment domain, right? A domain model is a conceptual model of the domain that incorporates both the behavior and the data, right? So that's Wikipedia I stole from. And also, I really like the talk from Colonel Elliott. He has been advocates for denotational design of software, and he also advocates functional reactive programming, right? So I got a lot of inspiration from him. Lastly, just for a teaser, I'm still learning all these category theory stuff, so I try to create a little bit of categories about money. I'm going to also talk about what's my view of what is actually called real-time finance using all the concepts I'm going to define today. So first thing, we're going to rethink about the domain of payment, right? So let's start with the journey. Let's think of some of the payment requests that you might you can imagine, right? So first, I think this is the easiest, right? That's how most people think about payments. So Bob requests to send $42 to Alice now, right? So there's components like whom, sender, Bob, amount, $42, recipient, Alice, and when, now, right? So that's a few components. Streaming, that's exotic concepts, all right? So like Bob requests to send a constant flow of money at $420 per 30 days. That's kind of like flow rate. To Alice now. So similarly, you have a sender, you have a receiver, and a rate instead of a discrete amount. It's a rate. A rate is measured by whichever comfortable to you for 30 days, per week. Per month is tricky. We have a very different days per month, right? So for 30 days is a bit more convenient. And also you can say when, right? So that's a now, right? That's a streaming. Another one, instant en masse. What do I mean? For example, Microsoft requests to send 42 cents per share to all its shareholders on the next X dividend date, right? So what's the component here? First, sender is Microsoft, recipients, all its shareholders. So it's no longer one-to-one, it's en masse, right? And the number is measured by, not amount, not the streaming rate, but 42 cents per share. So that's another way of measuring amount of money you should send, how it's sent. And the date is also no longer now, but the next defined date is called X dividend date, right? So but lastly, you combine two exotic concepts to become new concepts, even more exotic, streaming en masse, right? So let's pick the most bizarre guy here, which is Elon Musk, requests to send a constant flow of money at 4.2 billion per 360 days to all its shareholders. That's a lot of money, with individual flow rates proportional to their number of shares, right? Like dividends, it's proportional. And from 20th April, right, as example. So here you can see that there's a one sender, Elon Musk, and the recipients are all its shareholders. And the rate is measured by 4.2 billion per 360 days, a financial year. And the way to split the amount of money is proportionally by all its by the number of shares of each shareholders. Okay, so that's a lot of new concepts, right? So how do existing system cope with all these payment requests? Well, short answer is they don't. So financial market utilities, the FMUs, things like SEPA. I mean, while we live in Europe, we know SEPA system. It's pretty instant almost, right? So you can send a few seconds later, your counterparty receive it, but it has to be in euro. And target 2 is a similar it's a similar mechanism, but for different scenarios. From the other side of the pond, you have the US systems such like Fedwire, CHIP, SWIFT, all these kind of, SWIFT is international now, right? So these are all the so-called FMUs. Unfortunately, the footnote doesn't show here, so you can search for the keyword FMUs, right? Then you have the public blockchains and their token standards. We're talking about a Bitcoin, Ethereum, and all the ERC20 coins on top, token standards, that's by ERC20, right? So all these are also, let's consider them existing system in the context of superfluid concepts, right? So let's see how they cope with this, right? Instant payment. For the FMUs and for the public blockchain, they can handle, right? For the FMUs, usually quite fast within the same system, but it's kind of getting poor when you need to do interoperability, right? So if you send euros to United States or South America, you're going to experience the poor interoperability, right? So sometimes it's almost impossible. But that's where the public blockchain comes to the rescue, right? So yes, you can send money instantly across globe as long as there's internet. But sometimes with scalability issue, right? So we all know that Bitcoin, like every 10 minutes there's a block, things like that. So yeah, it kind of works, but there's a scalability issue still being kind of resolved by the smart people. What about streaming? Okay, so in FMUs, you could do that, but it's only in simulation, right? So it's microtransactions. You send small amount of money in a very frequent way. So it kind of simulated streaming, but not exactly, right? In the public blockchain space, microtransactions maybe, but can be very costly. I mean, only Ethereum, each transaction has at least a floor price, right? So if you do a very frequent microtransactions, it's going to cost a lot, right? But on Lightning Network, for example, on Bitcoin, then there's no such floor price. You can just keep sending, and if you're lucky with a routing that it doesn't cost any money or costs only a fraction of money, then yeah, microtransaction probably is going to work, right? But it's still very verbose. In a minute, we'll see. En masse, I would say it's almost not non-existing concepts. If you want to send all the dividends, it's going to be as many transactions as needed in the system, right? So it's not going to be expressed in a way that natively as en masse. You only can simulate the effect. In the public blockchain, in fairness, there are different ad hoc solutions. So, but I would not name it because I don't know all of them. But if you're familiar with the blockchain space, you might heard of some of the en masse solutions that you can send to thousands of participants, probably in a very scalable way, right? So there are ad hoc solutions. So that's a picture of what we have so far. So what is the ideal system here? What do we want, right? Let's see. A formally specified version, right? So a foundation designed using denotational semantics approach, right? That's what I think it should be ideal. I mean, we can borrow the idea from Colonel Elliott again. There's a wonderful video from him in Lambda Jam 2015. You could watch it later. It also built with compositionality in mind. We're in a functional programming conference, right? So this is a magical part. If you can make such system, that'd be great. So actually, Simon Peyton-Jones, if you're into Haskell, you probably know, you must know who's him. And he has been working for Microsoft research for a long time. Actually, I find this hidden gem only lately. He has a paper called Composing Contracts in year 2000, and he described potentially how do you composing financial contracts using combinators, Haskell, and it's a great paper. If you're interested about this topic, have a read. So the next thing is about efficiency. So all the things I described before in the existing system, there's no efficiency. Why? Because you're only simulating the effect. Right? I'm talking about a system that can interpret the DSL. So all those payment requests I described, you can think of as some sort of a proto idea of the DSL, right? So the kind of domain specifically of describing what kind of payments I want to express in the system. And perform those operations with as little possible the information waste. We want to be efficient here, right? So use micropayments to simulate flow of money? Nah, not good. So send dividends payments one by one to all shareholders? Nope, not efficient enough. So they're all too noisy. So our goal is to make an ideal system that is as least noisy as possible, right? So that's what I want to show you today, how to model that using a toy model, a specification, however you call it. So what we should build is design a denotational semantics for the new payment requests and expressive and composable DSL for the semantics. And lastly, a new payment rail that natively interprets and executes the DSL that with the 4 type of semantics I mentioned, right? 1-to-1, 1-to-n, instant, streaming, 2x2, 4 type in general. Okay, so let's try, right, today, design from bottom up in kind of layered approach. It's kind of conceptual layering, right? So let's start with syntactic level. So let's first ask question, how money should be presented in the system. So bear with me, I'm gonna introduce a lot of exotic concepts now. I try to go slow enough, but I will have limited time, right? So bear with me here. First, let's see. Let's call something value, right? Let's call it unaccounted value. Let's start with a very, very basic. What is unaccounted value? Okay, it's an integral and it has a default value. Done, right? So let's call it unaccounted value, right? Baby step. But the one problem is that there's no further type information about the value. So we can't express more information with this definition. So we kind of need to add some types. So the way I build it in the toy model is that let's give it some sort of tag, right? I happen to use just typable. Typable is more like a runtime information, but some people may say that maybe the sum type is better. Runtime information is probably more expensive, but that's not a concern, right? So in general, this is about adding type information to the unaccounted value. Let's call it accounted value, right? Accounted value, when it has some sort of type, and it's only should be only used by a specific subsystem. We'll describe what is subsystem later, right? I'm building up the concept, so bear with me here. Now there's a tapped, untapped. Okay, there are 2 classes of kind of values, right? One is tapped, one is untapped. An example. Let me just go straight to the example, right? It's probably easier. So in your personal account, let's say you have a bank account. What I mean here by untapped value is that the one that you can use immediately. But sometimes your bank also reserve some money you can't use immediately, right? So things like you made a credit card payments and you reserved, and until the other side either send it back to you or used, you can't touch it, right? So that's what I mean. So untapped is the one that all the subsystem can use, freely use. They're just there. And tapped is the one that there are certain subsystem kind of take hostage of it. And so it will keep it for a while until you can use it, right? So unfortunately, the code got cut off, but I don't think the details matter much. You just know that there are 2 types of values in general. Okay, let's define now a real-time balance, all right? Because now value now is kind of divided into different types, right? So I'm talking about a real-time balance. That is a functor, a container of those little values. It become from one single value to a vector of those values, right? And then there is a net value of that, so it converts from this vector to a single value, right? So that's a basic definition. And so just think that it's converting from one single value to a vector and back and forth, right? So that's all it does here. And it's a functor of these type values. Again, bear with me, we'll see why it's useful later, right? So another simplified view in the second bullet points I said is that you see that it's just an array of those values. Okay, so there's some law required if you want to define such thing is that, okay, first it's monoid, so you have left identity, right identity, and associativity. Okay, those are easy, get out of the way. Then you have if you convert from the single value to a vector and convert the vector back to the single value, they should be the same, right? So that's another property you should define. And there is also conservation of net value. So another set of functions, they also have this property. If you convert a net value x to this vector and convert it back to that single value, they should be the same. So that's another property. All right. Okay, so the next thing is now we have values. What about ownership? That is then the so-called money distribution. So there is a paper called Unifying Theory, believe it or not, Unifying Theory of Electronic Money and Payment Systems. And they actually defined the whole thing here. And they happen to be from Estonia. I came from Estonia, I live there. And I talked with the folks, I told them that this is not complete. We can define superfluid by adding something here. We'll see, right? So how they define it is that there's a set of monetary units. So there's a big set here, U. And they define two functions. One's a new function. That is the value function of each monetary unit. What is monetary units? The example would be a coin is a monetary unit, a banknote is a monetary unit, a bank account is a monetary unit, a crypto wallet is a monetary unit. A monetary unit has a value, so when you have a banknote, you know how much value it is, and you also know who is the bearer, so who is the owner of it. Basically two functions, right? It's a very pedantic way of expressing that in a way. So then when you talk about describe the system, you say we have a money distribution. It's distributed among the bearers, so basically the owners, and the value of each monetary unit, be it coins, be it banknotes, be it bank account, be it crypto wallet. So that's one way to see it. So I told the one that behind the paper is that, okay, the superfluid basically stealing your idea, but added context. Right? So all we did here is that in a new function, instead of just getting the value, you give a context, the CTX here. The CTX here, in case of superfluid, is simply the timestamp. So when you calculate your balance, it's no longer a simple input-output based on what's a monetary unit, but you also take into account of time. That's where the magic is. So when the context itself changes value, you don't need to do any transaction or any changes in this money distribution, and your ownership, your balance or your value is changing. So that's how it's built up, right? So in a moment you will see how actually it's done. All right, so let's review it. What we have built, what kind of exotic concepts we have built so far. So from top we got this unaccounted value, and then next we get the typed value. On typed value, we have two types. One is tapped, untapped, and then they become a functor of a real-time balance. Then you have the money distribution, then you have the money units. Okay, I hope this at least shows that it's not that complicated. Okay. Okay, let's now go to the next stage, right? So now we have a system that's describing that how money is represented. Next stage, we say, okay, how money should be moved in the system. More exotic concepts, bear with me. So let's define another concept called agreement. The idea of agreement is to represent something ongoing, right? So the thing about normal payments, there's nothing ongoing. I send you the money, you receive the money, done. There's nothing ongoing anymore. But in order to describe something ongoing, we create a new concept, new data structure called agreement. There are two parts of this. One is monetary unit data agreement. The other is the agreement operations. Okay, right. So the agreement monetary unit data is one that provides pieces of balance to your banknotes, let's say. Right? And because we're talking about the different subsystems, right? So they are all little piece of agreement monetary unit data, provide a pi function, let's call it, just make it a shorthand. It's balance provided by this agreement. All it does is give back a number called a real-time balance, and when you want to know what is your balance of this account, you simply sum it up, right? So you fold all the value, get all the little values from all the agreement, and you start with empty value, and that's it, right? So basically, you enumerate what agreements you have in your system, and sum it up, and that's your balance. All right. Okay, interrupt me if you want me to explain a bit more. I'm just conscious of time, that's why I kind of rush a little bit here. Another is agreement operations, right? So now, previously, we know that how to get balance from all those little agreements. But in order to change a state, we have to also define some sort of operations, right? So just think of this as you take the input as the input of agreement operations. You take some data. Also, very importantly, there is a time, right? Because everything we build here is about time in order to represent continuous relations. So the time is an input, and then it gives a new value for the agreement operation data, and also gives a delta of the results. Then because real-time because you can add value to the previous. Sorry, I think I forgot to mention. Because this monetary unit data is a monoid, and here by generating delta, you can then add back to it. So that's why it is like that. So it's probably a bit abstract at the moment, but I promise you will see why it's all like that, all the concepts building up. All right. So let's review a bit. What is agreement framework? So in general, you have monetary unit data, which is defined previously, right? So basically means how much money there is in this coin, or in this bank account, or in this crypto wallet, and they are just a sum of value from this little things called agreement. And in order to change the value, you use operation, right? So operation change the data for the agreement monetary unit data, then eventually it changed the balance for the monetary unit. And because the balance is also a function of time, that's how you would continuously receive money without doing anything in the system. So that's kind of continuous aspect coming in. Okay, let's first define, using this framework to define something called instant transferring, right? So this is basically what we do nowadays with payment. We want to express a semantic that party A is sending X amount of money instantly to party B, right? Okay, so how do we do that? Right? It's, well, built from lenses. Okay, that's scary. We'll show why it was like that. But lens is just a structure of getter and setter, right? So by having this abstraction, it will allow me to reuse this information later again, reuse this function again, right? So in terms of, if I want to send money from A to B, what I want to express is that when I do this transfer operation, right, because I need to define a transfer operation, all I do is I subtract amount of money from my sender and add that amount of money to my receiver. All right, then I generate this little delta, and by all the magic of functions, they add to the existing states, which means you subtracted this amount of money from your current account, from the transfer from account, and added that amount of money to the transfer to account. All right, a lot of abstractions, but and in order to combine the delta, you simply define, okay, I just over the value, I add the in order to combine A and B, I add the fields from B to the fields from A, right? So it's a very trivial operation, and the pi function is simply adding that field. That's it, right? So with all these abstractions, blah, 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 I mean, I just simply defined a one-to-one instant payment. What's the big deal, right? It's a kind of waste of time. So I basically here does transfer from Bob to Alice, $42, with all those 20 minutes of build-up. Waste of time. Okay, but now we have something new, right? Now we're going to use all this framework to define something called a constant flow agreement, which is a way to say a party A is sending a flow of money at a constant rate X to party B. How can it work in a nutshell, right? So A and B share the same context, which is a starting point, very important. The context is a time. So because they share the same context, when the time advances, think of blockchain, right? What's changing every block that you don't need to change state? Time. You query the block, what's timestamp? always changes, right? So that's the context that everyone can use. And because you've shared that, when the time advances, the A and B's balance move at the same rate, but in the opposite direction for both of them, right? Just for this one piece of agreement. And any party can have as many as such agreement ongoing, right? I can send to 10,000 people. And because it's a monoid, you combine everything into one anyway. So there's a net flow rate. Although there's 10,000 different agreements actually ongoing, right? So everything becomes a single value eventually. That's in the context of a constant flow agreement, it's actually just net flow rate intuitively. It's very scalable. That's the point. All right. Well, more lenses. In order to combine the information here, we have three key information about the constant flow agreement. One is when it's settled, what's the settled value, and the net flow rate. It's not very obvious here why I need to store three value, but just from three value, in general, in order to combine those three, you just replace a new settled at time with a new value, and for the settled untapped value, you just add on top to the previous value. For the net flow rate, you add on top of it, so it's a delta kind of thing, right? But here's a main function, how to make it work. So in order to, did I make it clear here? Oh, this is a calculate actually the balance off, right? So this little agreement is calculating how much balance of this constant flow is providing to the monetary unit, to the bearer, to Bob. It basically calculates, okay, the flow rate multiplied by the timestamp delta, the time delta, and plus the current settled untapped value. So that's how, when each time we query your balance of the account, because the T is going up, right? Your balance also goes up because the delta, this delta part is going up, right? So nothing else is changing, only this T is changing. And that's how your account gets either more and more money, depends on your net value, net flow rate, is it positive or is it negative, right? Another thing you need to define is, okay, what if we want to do operation called update the flow rate, right? Let's say Bob wants to send Alice $10 per month, but I'm changing to 20. So what I need to do is basically recalculate the settled balance and tracking the latest flow rate and checking what's the flow rate delta and create two delta for both sender and receiver. And these delta will be then add to their states, append to their state, right? So then they have a new state. After that, then they're going forward, and they have the state correctly reflecting the new flow rate between them, right? Okay. So that's it. That's how you use this framework to implement a constant flow agreement. Same exercise can be done. We actually have a prototype here. It's called decaying, right? Instead of constantly sending someone money in a constant flow rate, you can actually even apply the decaying flow, right? Which is a half on a decaying curve, right? So basically to have a limit of how much the other side will receive, but they will never receive that much money because there's half-life. So flow rate will half by a specific time. But basically the formula here is exactly the same as the decaying formula. So I'm not going there, just telling you that with the same framework, you could express a new type of a flow rate that is not constant even, right? So I mentioned this lenses thing, right? But why do I do that? Because remember that in the very beginning, I talked about that it's not only about one-to-one instant versus one-to-one streaming, but there's also one-to-n. So in order to reuse those informations, those functions that we created before, right, the constant flow, and so we basically redefine how those lengths actually, the getter and the setter is done. So there's a level of indirection there. So this is actually the trick to make it work, not only for one-to-one, but for one-to-n. So the way to look at it is that it's the same constant flow, but it's a family of them. So you give a different length implementation, and then the constant flow become either one-to-one constant flow or one-to-n flow distribution. We actually call it a flow distribution. It's like Elon Musk sending a stream of dividends to all his shareholders, right? So we reuse the same function here, but using the length to abstract how the getter and the setter is down, and then in the end it become functionally different semantic in terms of payments. So I think I'm going to start to skip things. So basically, there are two types of lenses defined in our system. One is universal lenses, which universal means that it's available for everyone. That's used to define one-to-one payment semantic. And the other one is proportional distribution, so that this is a way to describe one-to-n relationship, right? So we're reusing the same constant flow semantic, but describe one-to-n. So you have Elon Musk, which has one contract, and then you have all its recipients that it's like you can think of as a constant flow gets splitted between all those subscribers, right? So the gist is that it's a magic of length, right? Review. Let's have a look at what's all these exotic concepts about. So how money is then moved in our system then? So subsystems are created through this agreement framework. Each agreement will give you a piece of balance. That's called a pi function. And there's an omega function that transform data and create new information that a new monoid you can kind of append to your existing states. So, blah, blah, right? And we also use a length abstraction to kind of reuse some of the function to express different semantic, like one-to-one versus one-to-n. Okay. Notable agreements, we kind of mentioned a couple of them already. One is instant transfer. One is constant flow, like one-to-one constant money flow. Decaying, it's a possibility. And one-to-n instant transfer, right? So it's like one-to-one transfer, but you use length to split them into any number of participants, right? It's kind of one-to-n transfer. Same similar construct. You can then do split the one-to-one streaming into one-to-n streaming. Okay. I'm gonna really skip. Okay. Okay, so all those are just pure functions, but eventually we need to give some effects, right? So what are the effects we're talking about in the actual system? We need to be able to load some data from storage. In terms of blockchain, we need to load from blockchain, and we need to read context from somewhere. We need to also do authentication. We need authorization. Sometimes we also need atomic transactions so that if something fails, the whole transaction fails. Right? Well, actually, everything is defined as a token, as a monad, so that's how all the effects are eventually jammed into. All right, so you have two types of effects eventually you can create. One is token, right? One is note. Note is like a UTXO type of thing, and token is more like the Ethereum type of thing, right? You have a token and you have account. So that's the last stage. So implementations and plans. So all these are actually toy model, right? We actually only implemented on EVM. So early Superfluid protocol idea is implemented only for the EVM, and it's in Solidity language. Not all those fancy stuff mentioned is in this current protocol implementation. But it is live though, so the system is live. All the one-to-one constant, one-to-one instant, one-to-one flow are all implemented. Even one-to-n splitting of instant payment is also implemented. However, okay, also we also achieve things like $10 million streamed a month, 30K addresses in the system. So that's our achievement so far. The whole thing that I would describe in the very beginning is a Haskell specification or the toy model, just trying to kind of condense all the idea, and including some idea that we haven't implemented in the Solidity layer, in the EVM implementation. Right? Still work in progress, but already functional. Plan to fully support the semantic, which I actually had to skip. Plan to also work on the financial contract combinators, inspired by Simon Peyton-Jones composing contracts. I don't know, I think I will skip this one. Maybe just some joke. I actually just trying to add this just for this conference, how to think about the money, maybe using some category theory, but I'm not good at it. I'm just still learning, right? So here's from a famous Polish physicist. So he said that here's a categorical rule of thumb. Every time you have a composition, you should look for a category. Okay, category everywhere. Okay. The other is category theory is a study of compositionality, building big things out of little things, preserving guarantees, from Ken Scambler. I really like this quote also. Program search for compositionality. Well, it's a joke. He didn't say that. And also the dark side, right? So the category theories are intellectual terrorists, actually said by Philip Bordler from his video. So if someone telling you category theory and try to scare you, call them intellectual terrorists. All right, so maybe I'll just do real quick, right? So what we could, using category theory maybe to model something not really useful per se, maybe in the end, is like category distributions, right? We talk about money distribution. What about relationship between all those money? Well, the Federal Reserve's US dollar is backed by gold and a bunch of, actually mostly US dollar, US picture is missing here. It's not this one, actually. It's a government debt. And they are kind of backed, right? Backed by those assets. And then the commercial bank's dollar is actually backed by those. You are not using the same dollar. They all call dollar, but they're not the same, right? And then you have the US coins, right? They are backed by Federal Reserve money. Then you have Ethereum, which backing something called DAI. That's the algorithmic dollar. Then we have this one is like accounting domain, which what we did here is basically mapping the unaccounted value to right side, which is accounted value. That's the reason I use the word accounted value. So you have a real-time balance, which is expressing the idea of moving payments around. And you have then balance sheet. It's also kind of sub-accounts, right? So you have like, you're breaking an unaccounted value into a group of small values. And then the sum of it is the equity, right? The sum of the real-time balance is your balance. And then the sum of the income statement would be the profit and losses. So that's my way of thinking. You know, maybe all these accounting domain are just a functor of the left side, which is the unaccounted value. Then you kind of reconcile between one or the other, right? So that's what accountant does essentially. You reconcile your bank account to your balance sheet or your income statement, blah blah blah, right? That's one way to think about it. All right, I'm gonna jump to. Thank you very much. Thank you for your attention. So you can find all those things I talk about from our monorepo, Superfluid Financing on GitHub, Protocol monorepo. One of the packages is actually spec Haskell. You can download and run it, and everything what I said is it's not a lie. Presentation source also available in our wiki actually area. If you search for it, you probably can find it, or you can just check out this domain. Yeah, thank you.
Okay, you've got 5 minutes for questions.
Oh yeah, questions.
Yeah. Yeah. if you want.
I just run away now. Yeah, sure.
Hello. So you said you've implemented the EVM-based implementation of the flow. Mm-hmm. So how it would work? Because let's say I would like to open a stream of micropayment. So like let's say each rate is not enough to cover the fee on the blockchain.
Yeah.
So how it will go on work? Is it off chain? So unless I just pull, it will be No transaction?
Yeah, so we don't do micropayment, otherwise it wouldn't work, right? So that's essentially, we're using the function of time to actually give you a different amount of money that you own. So when you query how much balance you have for your account, it changes every block. Not every second, because on Ethereum, every block is every 10, 13 seconds, right? So that's how you get different money every block. So there's no micropayments. So now nothing is changing.
Every block there is a transaction and there is a fee paid.
There's no transaction. Every block, timestamp changes and your balance calculation changes. So you are calculating your balance through a pure function, almost like.
It's not the balance on the blockchain, it's balancing the...
Yeah. So if you're familiar with the Ethereum ERC20 standard, the balance of is a function.
Yeah.
So it's not a value stored anywhere. You can actually re-implement the function as a function. Yeah, that's a trick, yes. Yeah.
I think, is there someone up here who had a question first?
Hi, thanks for the doc. Have you thought of like generating at least some parts that you specified there to the smart contract directly?
Would be nice, yes.
Yeah.
Thought about it, but no, haven't.
Oh, okay.
Yeah, it would be nice, yes. Yeah, it's an open source project. Nothing here is a secret. I mean, really want to. I would just put a plug here if you really, if you want to kind of join the journey of Superfluid protocol. I mean, we are currently mainly on Ethereum, but you know the space is also big, so we might also move somewhere else also. Yeah.
So let's assume I have subscription agreement with you, right?
Mm-hmm.
And subscription is $100 per month.
Mm-hmm.
And then I have only $55 in my account.
Yeah.
So how do you detect that subscription should be terminated and I defaulted?
Yeah, good question. I hide that dirty little secrets from here today. It's because there is a little bit of off-chain kind of permission. It's actually decentralized in a way that once anyone detects that you run out of money, then they can come and delete that agreement between you and me. And in doing so, they will get a little reward. So that's what's built in the system, in the Ethereum version, for example. Right? So you can say, okay, you have subscription with me, you keep sending money every month, but if you run out of money, then that subscription will be deleted. Then maybe a backend service will send to my backend a notification, say, you run out of money, then I can send you a reminder, hey, add more money there. So that's the dirty little secret I didn't tell today.
Yeah, hi. Sometimes we have the systems when you don't own the user's account. As example, the credit card payments. How we can use this model for that type of payments? Right.
So in the Ethereum implementation, because we're already dealing with the last stage, the effect, right? So we actually have a system called a permission control or access control list. So you kind of delegate some of the power to external controller so they can update your account on behalf of you. So you kind of either cryptographically or either as a off-chain agreement or something, but there is on-chain a permission that you allow a third party to update your account. So that's how it's implemented.
I just want to take a second to make sure there's no online questions being asked. No? Anyone else in the room? No? Okay. Well, thank you very much. Unless. Oh, one question has just popped up online, I'm afraid.
How can people contribute? Good question. So, couple of links. GitHub link. The organization is called Superfluid-Finance, and I think we have the monorepo pinned up there, so you can easily find there. You can also go to our docs.superfluid.finance to learn more about our Ethereum implementation. But if you like Haskell and all this stuff, come to our monorepo. Maybe you want to port this to, I don't know, maybe Cardano or whatever. So there's lack of resource at the moment. So if you want to contribute as an open source project, come to our monorepo. Yeah.
Brilliant. Can we get another warm round of applause for that fantastic talk?